Let's look at an example of an application of derivatives to the devaluation of an item over time. So you know the saying that if you buy a car, it loses half its value the second you drive it off the lot. Or basically something which is used loses quite a bit of its value right away. But it also retains some of its intrinsic value for being used. Like a car, as it gets older and older, it doesn't really get that much less valuable. I mean, there's other variables at play, such as mileage and so forth. But let's just assume but basically you could use a reverted logistic function, which is what this function p is, which is fairly common. But essentially it has a very, very sharp exponential decay. Or this one is not exponential, but it devalues very quickly at first and then flattens off towards a horizontal asymptote, which can be described by functions such as this one. And we won't get into why this particular function makes sense here, but essentially we have this very steep decay, and then it sort of levels off towards its eventual long-term value. Like say you imagine in this case it's going to start at a value of 70,000. Let's say that this was the price of an Escalade. At the beginning it's starting up here at 70,000, and it's decaying quite rapidly to some point where and another question is what's the limit of this over time, or what's the eventual value. We could kind of look at that if we examine this a little bit further. But first question, it says find p prime of t. So if we wanted to know, remember a derivative in the last week or two, we've been focusing so much on how do we find derivatives using things such as the power rule, the coefficient rule, the sum rule, the product rule, the quotient rule, and the chain rule. All of those are fundamental rules for finding derivatives. But remember, derivatives are meaningful because they help us figure out the rate of change. What is the slope of the function at a point in time? Or finding a tangent line. All those things are why we care about derivatives. And there's even more reasons beyond that. But let's just kind of practice in this particular case. So first of all, finding p prime. Well, here we have 70,000 minus this whole thing. Well, for derivatives, we could take the derivative of each component separately because it's a difference, and we could just take those two completely separately by the difference rule. Well, derivative of a constant is just 0, so I could write that, but I'll just go ahead and skip that. But basically, that would turn into 0 when I take the derivative, and then I need to take the derivative of the second part. So this is a division of two things, so we could use the quotient rule here. Low d high minus high d low, square the bottom, and away we go. And it would be negative because there's a negative out front. So let's go ahead and write it. So I have low d high, and low is a square, so I need to remember to have all of that. The derivative of the top would just be 500,000 t, and this would be minus low d high minus high d low. So high is 250,000 t squared times the derivative of the bottom. And notice the derivative of the bottom here, this is a power of something else. So when you're taking derivatives, even when they're within other rules, if you notice that we're using the quotient rule here, I can't ignore the chain rule. The chain rule still applies in these sorts of instances. And actually, let me move this over a little bit. So that I have a little bit more room to write. I know you guys can't do that in your notes, but basically I have low d high minus high d low. And here, d low, I need to use a chain rule because I have 2t plus 1, and it's within another function. It's all squared. So d low will be, I could drop the power down, 2t plus 1, and the power would now become 1. So I could just skip that, but basically drop the power, subtract 1 from there. But I need to multiply by the derivative of the inside by the chain rule. And since it's just a linear function, 2t plus 1, the derivative of the inside is just 2. But this is a very easy thing to forget. Something that is missed very often when I see students taking derivatives is remembering to use the chain rule. And that's just when I'm taking a derivative with anything besides just the variable within in the parentheses, you always have to multiply by the derivative of the inside to cover your base. Now we're good to go. And again, we would need to square the bottom, which would become to the 4th power. There we go. So derivative here is quite complicated, but that's okay. And let's go ahead and clean it up. So on the top, and it probably was smarter just to expand the denominator instead of, so we didn't have to use a chain rule. If I was just to multiply this out first, I wouldn't have had to worry about it, and that might have made my life easier. But actually, one thing that makes this particular example a little bit easier is notice that there are two bigger terms on top, and it's actually a common factor to the bottom. So there's a common factor within the three terms of 2t plus 1. And we can actually use we can actually cancel one of those factors from everything here because it is common across all terms. But you want to be careful because normally, as I said in class, you can't do that sort of cancellation with the quotient rule. Normally that doesn't work. But here it does. And this just makes our life a bit easier. So I have 2t plus 1 times 500,000 t. So that would give me 1 million t. And there's again a negative out front. 1 million t squared. And that would be plus 500,000 t. And then that would all be minus what I have on the right-hand side, which is 2 times 2 times 250,000 t squared. Actually, notice that that makes 4 times 250,000. This would just be minus 1 million t squared. So actually, this whole, I have 1 million t squared minus 1 million t squared. This actually just becomes only the 500,000 t. Since this first distribution cancels with all of that. And then that would all be divided by 2t plus 1 cubed. And so the derivative, while it looks quite horrible, it actually ends up being relatively simple comparatively at the end of the day. So let's answer some of the questions that were asked about this. And this will be a commonality with your homework. Usually at the end of each homework assignment, there's one or two applied questions where we put all of the practice we put into practice. We use those things that we've been covering mathematically speaking. So first it asks us, what's the price of the item after 4 weeks? How about a year? And this just gives us a sense of how the value of whatever the escalate or whatever we call it is going to be. But the price after 4 weeks, and notice it says t is in weeks, so I would just use 4 in there. Well, I would have 70,000 minus 250,000 times 4 squared. Let's go ahead and do that in the calculator. 250,000 times 4 squared. And that would all be divided by 2t plus 1 squared, which would be, so I'm getting a call once, I'll answer that in a minute, which would be 9 squared. And so that would leave me with $449,382.72. So I'll just go ahead and round it to the nearest dollar, or the nearest cent, I mean, since this is a price example of an item over time. And, we could estimate that to be, well, I need to do 70,000 minus that answer, which comes out to be approximately $20,617. I'll just round off the change because it's a pretty big number anyways. But obviously, I could be more accurate if I wanted to, or if I was instructed to. And then it says, well, what about after a year? Another way to make this a little bit easier is if I, I'll just forego the graph because that's going to take even a bit more time. But that would be after 52 weeks. So what's the price after 52 weeks, and how is this valued even further on? So like looking at this example, after 4 weeks, it has lost quite a bit of its value already. But what about, much further down the road later on? And notice I did not actually label this graph, which was poor practice by me. But if you graph it yourself, you can see, start at 70,000, it decayed very, very quickly down to about 20,000. Where will it be at later? Well, I'm going to have 70,000 minus 250,000 times 52 squared divided by parenthesis 2 times 52 plus 1 squared. And anyways, the value, I missed a 0 in my 250,000, which is why the answer doesn't make any sense. Let me go ahead and fix that. And it's going to be worth approximately $8,685 after 1 year. And this might not exactly make sense for an Escalade to be devalued this quickly, but again, some items, the speed at which it decays will change based on what type of item it is. Some items lose their value very quickly, and some take longer. And so that's kind of what brings up the next question. So what is the rate of change of the price after 4 weeks and a year, and what does it represent? Well, these sorts of questions you can always answer by using the derivative. That's what P prime does. It tells us what is the slope at any time t. P prime of t represents slope, or change instantaneously. So if I wanted to know what's the slope at this point in time, it looks like it's changing pretty rapidly in value at that point in time. Its rate of growth starts off, it decays very, very fast, and then it kind of slows down over time. And as we get to the point later on, 52 weeks, it's not really decaying very rapidly. You can measure those things by average rate of change, but a derivative gives us point slope at an exact point in time, or instantaneous rate of change, which is even easier because I don't need to find 2 points and average it out. I get exact slope based on the derivative. So basically this would be answered by P prime of 4 and P prime of 52. Those tell us how is it changing at this point in time instead of what's its value at this point in time. So P prime of 4, I would need to plug 4 into my derivative instead. So I'd have negative 500,000 times t divided by 2 times 4 plus 1 to the 3rd power. And this would give me my derivative at 4. And that's comes out to be approximately negative $2,743. And actually, another question is, what are the units of a derivative? Like, how do I describe what it means? But it's a rate of change based on time. And since my time variable was in weeks, this will be dollars per week. So I don't want to answer this as just dollars because it doesn't have the same units as the original problem. It's always a ratio of the original units to the units of x. That's why we often call it dy dx. The unitary answer will be in units of the original units divided by the units of the input x. And that's something that is not always obvious when it comes to functional notation. But essentially what this is saying is this item is losing approximately $2,000 to $3,000 in value every week. Pretty extreme loss in value. And by looking at it, that makes sense. Like, it's dropping very, very quickly. You could obviously just see what is the price after 5 weeks, but that would not be an instantaneous rate of change. It would be averaged, and that would actually be a little bit lower. And again, looking at after a year, we'd expect this to be much less rapid decay because it's sort of it doesn't lose much value over time. It's sort of capping out on some long-term value. But again, if we change our derivative and we plug in 52 instead, I'm just going to take the same formula and just at 52. What it would give me is approximately negative $22. And again, I'll just leave it rounded to the nearest dollars. And again, that will be in terms of per week. So what that's saying is that this escalator, whatever the item is that's losing its value, it'll only be losing about $22 in value per week after a year. And again, that rate will probably slow down. But again, we can see that this same idea applies to any function. If I know the function that predicts the value of the item over time, I know how the derivative tells me how much it's changing at each point in time, which is obviously something that's useful to know. It's useful to know the speed at which it is losing its value. Like, let's say we wanted to resell it or do mathematics behind buying and selling items. Knowing these sorts of things could be very important for trying to figure out when's the best time to buy or sell.